Hello, everybody. So in this lecture, we consider some application of the distribution theory to constant coefficient PDEs. So let me start with some notation. So first thing I want to introduce is partial differential operator. So I denote it by P of D. So P is a polynomial of D variables with complex coefficients. So in other words, P of X is written as the sum of multi-index with length less than or with normal less than or equal to m. A alpha, which are complex numbers, and x to the alpha is defined in the Euro way. So if x is x1, xd, so d variables, alpha is alpha 1, alpha d. So this is in n to the d. Then x to the alpha is defined by x1, alpha 1, xd, alpha d, the product. Okay, so once this is defined, we can define the P of D operator, which is a differential operator. When it applies to a distribution, it's given by the formula exactly the same way as how we define this polynomial, but we replace this x variable by this partial derivative, this d variable in here, so that we have a partial differential operator. It is linear because it's a linear combination of different partial derivatives. And it is called a constant coefficient because these A alphas are complex constant numbers, which are complex constant numbers. Okay, so our goal is to study the linear PDE of order m with constant coefficients given by this equation 2. We call it equation of order m because this m is precisely the size of this multi-index alpha defined by alpha 1 plus alpha 2 plus alpha d. So this whole thing, the sum of all the derivatives is less than or equal to m. So we call it PDE of order m. Constant coefficients just because we have constant coefficients. So here, this equation, the f function, or the f is a distribution in omega, which is known. So this is a given. This is something we know from the problem, and we would like to solve for u, which is in the space of distributions in omega. For instance, we can consider the fundamental example we have in mind is the Laplacian operator denoted by delta. And in this case, the polynomial is nothing but the Euclidean norm of x to the square. So in other words, it's x1 square plus x2 square plus xd square. Okay, so this operator is very important in the sense that that it appears everywhere in mathematics, in physics, and one of the reasons is that this guy is isotropic with respect to the derivative is isotropic in the sense that it's polynomial. Here is isotropic. So if we do a rotation for the variable x, it doesn't change the value of it doesn't change the Euclidean norm, right? Rotation doesn't change the Euclidean norm, so that this is invariant with respect to rotation. This could be very useful in modeling many phenomena. Okay, so the one of the most important notion in understanding linear constant coefficient PDE is the fundamental solution. So fundamental solution is defined to be the distribution in RD such that this partial differential operator PD applied to E gives a direct function on 0, so direct mass at 0. So this is a very important. The importance of this solution is reviewed by the following proposition. So let's just show this proposition 11.2, and it says that if we can find a fundamental solution, then we can solve the non-homogeneous equation 2. Whenever we know the fundamental solution E, then we can we can do a convolution, and this convolution will solve this linear equation. So let's give a proof. So for any, of course, in order to make sense of this convolution, we need some condition, and this condition for f will be it has compact support. So this is nothing but the distribution t in d prime omega such that support of t is compact. Okay, this is our notation for the compact supported distributions. If f is has compact support, then and E, let E be a fundamental solution. Of this operator, then we know, first of all, we know that this guy is well defined. These two guys are convolved because one of them has compact support, right? So is convolvable, and this is a well-defined distribution. This is the first thing to start. Now we check that this guy solved that equation too, right? So to this end, we compute a PD of the convolution. And from a previous result, we know that we can actually pass the derivative inside the convolution to pass any one of the distributions, and we still have identity, right? So we can pass it to the E with the fundamental solution. We pass it to the fundamental solution because we know that PDE is delta function by the definition of a fundamental solution. Then we have this delta naught convolve with F, and this is nothing but F because delta naught is a unit element in for convolutions. And that's it. So this shows that E convolve with F solve this equation. This is no homogeneous equation, and we're done. Okay, so now that we know that fundamental solutions are important for constructing a solution, it is of interest to ask whether or not a fundamental solution always exists, right? So, and it is a non-trivial fact. This fact was proved long ago by these two people independently, and they show that every non-trivial linear partial differential operator with constant coefficients has a fundamental solution. Okay, so fundamental solution always exists, at least in this case, in the case of constant coefficient partial differential operators. Okay, so this is reassuring. So what we are going to do next is to focus more on this this fundamental example that we have in mind, which is the Laplacian. So it's Laplacian. What is the fundamental solution of a Laplacian operator? And that's our next goal. In order to show this, we are going to make use of the Green's formula that we have already covered before. So this is a lemma. Okay, this lemma is a consequence of Green's formula. Let's see how we can do this lemma. 11.4. Show this tool. So this lemma says that if we integrate phi Laplacian u minus u Laplacian phi, we integrate it on the domain omega, which is an open set of class C1, then it is equal to the integration on the boundary of omega of some quantity which involves less derivative with respect to the surface measure on the boundary. Okay, so this is a strong reminiscence of the Green's formula or the divergence formula that we have considered before. So let's prove this this fact. So first observation is that we can always write Laplacian, which is given by I from 1 to the second derivative with respect to the I variable. Okay, and take a sum, we have a scalar. So this guy can be written as the sum I from 1 to d, so di, di. We can do the partial twice, right? And this is nothing but the divergence of the gradient operator, okay, according to the definition of divergence and gradient. So, so we make appear this this divergence operator, which would be useful. Okay, so now, so another formula that might be used is this product formula for divergence. So if we have a real valued C2 function, say, and the vector field RD to RD, also C2, then let these two function as such, then if we compute the divergence of the product of the new vector field given by the product, then it can be written as the gradient of phi, then inner product with phi, and plus phi divergence of capital phi. Okay, so this is simple. This is just a Leibniz rule, actually. Just to write it out and check it is exactly as this one. So now we can prove this this lemma. So we first consider the first term on the left hand side, which is the integral of phi Laplacian u du. Okay, our first task is to write it as the divergence of something, right? So for to this end, we're gonna use the second fact I just mentioned. So we're in this form, a real valued function times the divergence of something. Okay, this is the Laplacian of u is nothing but divergence of the gradient. So we're in this situation, so we'll make use of that, and we're going to have this divergence of this phi times the gradient of u, which is the vector field, and of course this is on the wait a minute, this is still on the domain omega, so dx. So this is dx, and then minus omega, then the gradient of phi, and the vector field inner product with that vector field, which is the gradient of u. And that's it, so dx. So now we make use of the divergence formula for the first integral, and we're going to have an integral on the boundary of omega, and this now becomes a phi gradient of u inner product with the outward vector field, the unit vector field, n x. Then integral with respect to the surface measure that is denoted by d sigma. On the other hand, we have exactly the same thing. I don't change the last term. And this is it for the first integral. And we are pretty close because we make this term appear. This is one of the term. This is the first term on the right hand side. Okay. So now if we do the same trick, but instead of using for the phi Laplacian u, we apply the same trick to u Laplacian phi. So then we're going to find something very similar, but symmetric. We kind of interchange the role of u and phi. So what we're going to find is the following. So we have this omega, so right hand side, the second term, so u Laplacian phi, and this is given by now still use the trick with this divergence formula. So we're going to have the integral on the boundary. So this time, so we're going to have a u gradient phi and outward unit vector field d sigma, and then minus omega delta u, it's gradient u, gradient phi dx. Okay, so now we compare these two terms. We realize that so this guy here, will cancel with this guy if we take the difference. Okay, and what we have will be this minus the same quantity with u Laplacian phi equals to this guy minus this guy, and this is precisely what we want. So the proof is done. Okay, so now we move to the proof of proposition 11.5, which gives the precise form for the fundamental solution of the Laplacian. So our first observation is that these guys are clearly L1 log functions. So around zero, there's no singularity, right? So this is integrable, and this is really this is also everything is integrable. So in all dimension, we have a L1 log function, which is associated with the distribution naturally. And this means that our first requirement is satisfied. Okay, at least we have a distribution. So next thing we need to check is that this guy, if we take the Laplacian, we should have a direct mass on the point zero. Okay, so our strategy for proving this formula is to refocus ourselves on the case of radial functions. Okay, because this Laplacian operator is isotropic, and it makes sense to search for a radial function. So this is our strategy for the proposition 11.5. Search for radial functions, radial function solution. And so that means that we are going to find the f, which is defined on r plus to r, such that this ed of x is nothing but f of x in absolute value if d is equal to 1, or the Euclidean norm of x if d is higher than 1. Okay, so this is our goal. So to this end, we need to. So what we have in mind is that this guy should satisfy this equation, right? So what we need to do is to take the Laplacian for this radial function representation for the elementary for the fundamental solution, and we are going to compute this this gradient f. So let's compute the gradient f. This is the first step. Compute this. Yes. Okay. Gradient of f of this guy is actually the composition of two functions, right? Function that maps x to the Euclidean norm of x, then f maps a real number, a positive real number to a real number. The composition of two functions. We're going to make use of chain rule to compute it. So by chain rule, we know that partial first derivatives, for instance, so becomes I of this guy is just the f prime of this, then xi x. But this is nothing but x prime of x, xi over the Euclidean norm of x. So if we take the second derivative, okay, we put one step further, and we should have so if we take the second derivative, then the partial derivative of Euclidean norm of x, we are going to have xi square x square. Okay, so then we can also take a derivative. We keep this guy, and we take derivative for the ratio xi Euclidean norm of x. Then we have 1 over x plus xi. We keep xi. Then we got this negative. I think we got negative xi over x cubed. All right. So now if now we can put things together, put the d terms together, okay, and we're going to have this f double prime x, and sum of everybody in here gives precisely 1, so it doesn't matter. Then we consider this term. We are going to have plus f prime Euclidean norm of x, then the d times the same thing, minus, actually, here becomes a minus, and sum over I, which gives exactly x, Euclidean norm of x squared divided by Euclidean norm cube, so we have this 1 over x. So eventually it becomes double prime Euclidean norm of x plus x prime of times d minus 1 over x. This is it. All right, so this is our first step. We compute this gradient of a radial function composed with the Euclidean norm of x, and we find precisely this guy. So now our goal is actually to find a value 0 outside of the small interval around 0. And that is because we want to find a fundamental solution, which is the delta function. And delta function, if we restrict it to open set away from 0, okay, so if we remove a small neighborhood of 0 from the RD, then the restriction of this distribution to that open set is equal to 0, identically 0, right? So this guy should be equal to 0 if we consider a domain which is away from 0. So here's our goal. What we do is to now step 2. Okay, let's move on. Step 2, we are going to let this guy equals to 0 in the domain. This omega will be RD with 0 removed. Okay. In this open set, we know that Dirac mass is equal to 0. Right? Restricted to this set becomes 0. So this must satisfy this property if it is the fundamental solution. Okay, so let's solve this this equation, and we already know that this guy equals to this quantity, right? So since this guy is just a variable of is a function of one variable, it's defined on the R plus with 0 removed. So we should have, then we have that f prime of R plus f prime of R d minus 1 over R is equal to 0. Okay, so this is our equation. So that we can find this f prime of R must be a constant times R to the negative d minus 1, right? So because of this form, we can easily guess the solution. So this is constant times a polynomial. We take the partial derivative. We could just take the derivative. We're going to see that this becomes we have this d minus 1 which appears, and if we divide it by and this power becomes d r to the negative d, and yes, to negative d, then that one will be cancelled out with this guy. Sum of everything will be equal to 0. So now we can solve. Of course, we can solve this differential equation. So this is given by the solution a constant times. So it depends on the dimension. So if dimension is equal to 1, okay, here we have already need to distinguish the dimension in this step. Okay, So if d is equal to 1, then so this guy disappears, and we know that the solution of this will be a linear function. So f of r has to be a r plus b. Just a linear function. We take a second derivative, we have 0. So if d is larger than or equal to 2, now we are in this situation. We're in this situation, and so if d is equal to 2, then we have this a times the log of r plus b. Now this derivative gives back to 1 over r, a constant times 1 over r. On the other hand, in d larger than or equal to 3 case, then we should have just another constant r to the negative d over 2 plus b. Right? Exactly. So we can find is our f of x to be just x absolute value if d is equal to 1. So this is our natural candidate for a fundamental solution in one dimension. We might need to work out the constant, but for the moment, let's just remove the constant. We just take the constant equals to 1. And we're going to remove also this constant b. We take b is equal to 0 because this is not relevant because after we're taking derivative, this will not contribute anything. And we take the constant a equals to 1, c equals to 1. So the natural candidate in one dimension will be, as I said, it's a linear function. When this a is equal to 1, b is equal to 0, we have this absolute value of x. Okay, and in 2 dimension, the natural candidate would be a log of x in absolute value, or no, in Euclidean norm, if d is equal to 2. And in higher dimension, the candidate would be this 1 over x to the d minus 2, and if d larger than or equal to 3. Okay, so this, according to our reasoning, will satisfy this this property. Actually, the Laplacian of this guy in this domain, this open set, Rd with 0 removed, is equal to 0. So in order to finish, we still need to show that this guy as a distribution on the whole domain Rd satisfy the equation we want, meaning that delta f is equal to the delta function at 0 if we consider this as a distribution in the whole domain Rd. So first observation is that this guy is L1 log function, so we can just we can give a value, any value for f of 0. We can call f of 0 equals to 0 for each of them, so that this guy, for 3 of them, all the situations, we have a function defined on the whole domain, the whole domain Rd. Okay. So then we need to check that if we take the Laplacian, we should have this delta function on 0. That's the purpose. So now we compute. So the next step is to compute Laplacian of f as a distribution on Rd. Okay. So in one dimension, that is pretty simple because the second derivative of actually it's just the second derivative of this absolute value function. So we should have the indicator x plus 1, x larger than 0. Then we have 1 less than or equal to 0. We have negative 1. That's the first derivative. Then we take a second derivative, and this is pretty much like the Heaviside function, right? There's a jump. There's equals to negative 1 for the negative part of the real line, equals to 1 for the positive part of the real line. There's a jump at the point 0, and the jump size is 2. So this is nothing but twice delta naught. So this is jump formula that we proved before. Okay, so considering this two factor, and in other words, we need to divide this guy by 2 so that the second derivative of this guy in the sense of distribution is equal to the delta function. So this gives the first result. E1 of x has to be 1/2 absolute value. So now let's consider D in higher dimension. So this is a much more complicated than just this small calculation. So to this matter, we need to make use of that lemma, that Green's function, Green's formula consequence. So first we consider any test function, right? So let's check the formula for any test function phi omega d prime rd. Okay, it's a test function rd. Say it is contained, the supported phi is contained in a certain open ball of radius r for some. Okay, since it has compact support, so this definitely is true for some r. So now we are going to compute this quantity. So this, so let me just write this f. We want to compute. We want to know, understand this Laplacian f, and we want to apply it to a test function. So by using the definition of the partial derivative, we can pass all the derivatives to the test function phi, so that we have f applied to Laplacian phi. Okay, so it's the first step. And now recall that all the function f are defined as L1 log function. It's given by as a L1 log function here, so that this guy is actually an integral. So integral of f of x gradient Laplacian f phi of x. So we consider domain of integration omega, which is let's just call this guy omega, which contains the support of phi. So we do not lose anything by computing the integral on omega, which is big enough, which is a big ball. So now the x, so this is what we want to compute. Recall that this guy can be written differently. This can be written as such as this guy plus an integration on the boundary of the domain, then with respect to the surface measure. But the thing is that we need to have C2 functions in order to apply this this formula. And here we have only L1 log function. So this is not enough, at least not enough is sufficiently smooth at the point 0. So 0 is the point. Everywhere else, these functions are all C infinity function. But on the point 0, there's some problem. So our idea is to make use of this dominated convergence theorem to approximate the domain. So here's the idea. We're going to show, we're going to just compute the limit when epsilon goes to 0 of omega r epsilon, where omega r epsilon will be the big ball minus the small ball. Epsilon is smaller than r, of course. On this, then f of x phi dx. So this is by dominated convergence theorem because we have some function with compact support. This is really nice function, and this is a locally integrable function. So we can do this, right? By dominated convergence. Okay, so this is approximation. So now our goal is to use Green's formula, use the consequence of Green's formula to this quantity. Okay, so let's do this. Now we have integral omega r epsilon of this function f of x Laplacian phi and this is equal to the same domain, R if shown, then Laplacian F times just the regular product. It's not a scalar product. Phi, then plus integral on the boundary of, we should have F gradient phi and R if shown, and this unit normal vector field pointing to the outside of the domain, and then d sigma, the surface measure. Okay, let me just put the surface measure in the end. So we have this minus. So now phi gradient F and d sigma. D sigma is the surface measure on the boundary of the domain. Okay, so now we are good. Let me make a few simplification. So first observation is that on this domain, the function f, since we have already checked that is the function f is satisfied for the fundamental solution, that equation associated with this fundamental solution, meaning that the Laplacian f is equal to 0 for any point outside of, for the region RD with 0 removed. In particular, on this domain, which is the subset of the set of this RD with 0 removed, this guy is equal to 0. So we can actually remove it because this is equal to 0. Right? So this is equal to 0. So the whole thing doesn't matter. And on the other hand, if we do some calculation for each of the terms, let me just write things out explicitly. So there are several things. Okay, let me just write it here. So first important thing is that the boundary of this domain is composed of the surface of radius r union the surface of radius epsilon. Okay, there are only two parts. And this function, on the other hand, this function phi and the gradient of phi all has compass support. We have already assumed that this function has support included in this big ball of radius r. And when we consider the integration on the boundary SR, which is the surface, okay, the surface of radius r, this guy must be 0. Same here, the gradient of f. So we know that the derivative does not increase the support, right? So still, the support of this phi functions has support still included in the open ball omega, the open ball omega. And on the boundary, these two guys takes the 0 value. So in the end, it remains only, so these guys are 0 on SR. So in the end, we can forget about one of the boundary and remains only one boundary, which is the surface of radius epsilon. And that's the thing here. We're going to proceed. Okay, so what we have, in other words, let me just write it out. We want to compute this guy. We call that, this is our goal. And this can be written, so this can be written as only one integral on the surface of radius epsilon. And surface of radius epsilon. And we have that term, which is f gradient phi minus phi gradient f inner product unit vector field d sigma. Okay, this is what we have. Let's proceed. Still one more calculation. So we need to know what is this unit vector field on outward unit vector field, and recall that this is our domain, and domain is composed of domain is analogous, So the boundary is composed of S if shown and S capital R. So there are two things. Now we're considering this S if shown. And the outward unit vector field is actually on this point, for instance, is pointing to the inside, pointing to the origin. And any point on the boundary of this SR is pointing to the outside. Okay, so the outside for the point on the bigger sphere is really pointing to the outside, to the infinity. And on the other hand, the outside for the inner circle is actually pointing, this unit vector is pointing to the origin. That's the difference. So now we are on this inner circle, inner sphere. So our normal vector field, outward normal vector field, is actually given by negative x over epsilon. So this is just the size, right? So this epsilon is just the size of the Euclidean norm of the vector x. Okay. So now, so I mean be precise for any x in S epsilon. Okay, so this is something that we are going to make use of. On the other hand, we also have what we need. We also need to compute, compute the gradient of f. So f is given explicitly. So in 2 dimensions, it's just a log function of Euclidean norm of x. So in that case, in that case, we should have this x over Euclidean norm of x squared if d is equal to 2. And if d is larger, then we have a polynomial, right? So we just do that calculation. We're going to find a negative d minus 2 x over x to the d larger than or equal to 3. So in any case, we always have this formula x over Euclidean norm of x to the power which is equal to the dimension. Okay. The only difference is that in 2 dimensions we have this constant equals to 1. In 3 dimensions we have constant equals to -1. 4 is -2, etc. Okay. So the constant, let me just call this guy CD x over x to the d to be to simplify some notation. So here CD is equal to 1 in D is equal to dimension 2, and it's equal to 2 minus D if D is larger than or equal to 3. Okay, so I think we're ready. We can continue this calculation. So let's call this guy star, and the star will be equal to, so it's an integral S epsilon. So F is a radial function. So S on this on the sphere would take the value just the f of epsilon, right? So it's okay. Let me maybe just write it more precisely. So just to write f of x to be gradient of phi, and then we have inner product with this negative x over epsilon. That's the first term. On the other hand, we have this phi x, and the gradient gives x over x to the d, and we have a CD, which is a constant, and times again negative x epsilon. This is the inner product, this guy. So the whole thing with respect to the surface measure on the little surface S epsilon. Okay. So the observation is that on the circle, this guy will be just a function of the of epsilon instead of the position, the precise position of x on the sphere. So so in other words, this guy is equal to log of epsilon. Sorry, log of epsilon without anything, just log of epsilon. In 2-dimension, and this guy would be epsilon to the negative d minus 2 if dimension is higher. Okay. So what we can do is to make a variable change. So what we can do is make the following variable change, and we're going to have this s d minus 1. This is a unit sphere in unit sphere in RD. So we can put the negative sign in front of the integral, and so it will becomes epsilon to the d minus 1. Okay. Then we have this, so whatever we want for this f, let me just call this guy, the formula in red is denoted by f epsilon. Takes different form in different dimension. So times gradient phi of this, it becomes epsilon w, and we have this time inner product with w, sigma dw. Okay, so here I make a change of variable so that we have additional factor epsilon to the d minus 1. Okay, so the point is that if we combine epsilon d to the d minus to the power d minus 1 with f of epsilon, which is given by this formula in different dimensions, this guy will eventually goes to 0, right? And this guy, if we compute just the integral with respect to w for everything inside, when epsilon goes to 0, this guy becomes a constant, just the gradient of phi on the point 0, inner product with w, and this guy will be just a bounded value. It's bounded by some constant, and this will go to 0. So the first piece doesn't matter. Okay, so eventually the first piece will go to 0. Let's look at the second piece. The second piece, we're going to have this plus, and since we can pull out the CD constant and integral, again, I make a change of variable, and I should find the phi of epsilon w. And here I got x, so x inner product with x, which gives the Euclidean norm of x squared. And so now we have this Euclidean norm of x to the power 2 minus d, okay? And on the circle, it takes the value of epsilon to the power 2 minus d, okay? Combine everything together, and we should have epsilon to the negative d minus 1. And then the variable change will contribute d minus 1, e to the d minus 1, sigma dw. And these two guys cancels each other. Okay. And when epsilon goes to 0, this guy, the phi function, will go to its value at the point 0. And this whole thing will go to CD eventually. First term goes to 0, second term goes to CD times phi of 0 times the total mass of the unit surface. All right. Okay, so we're done, because this is exactly what we want to show. We want to show that this guy, is a point mass at the point 0. And what we want to achieve is to show that this guy eventually equals to phi of 0 times some constant. And this is what we have. And the constant is the thing we need to divide it for the function capital F in order to have a fundamental solution. So this actually implies that eventually the fundamental solution for d larger or equal than 2, the fundamental solution will be given by this log of x divided by the constant, which is given by, look, the constant will be just CD, which is equal to 1, and divided by sigma, the total mass of the unit circle in which is given by, which is 2 pi, So the first case, d equals 2 case, is given by the log function divided by 2 pi. And in higher dimension, we have a different constant, and this constant is 2 minus d times the total mass of the unit surface, then x d minus 2 as desired. And let's finish the proposition. Okay, so now that we have quite precise information about the fundamental solution, okay, we can actually make use of this kind of information to deduce some regularity property for the solution, for the general solution. Okay, in here, for the solution of this kind of generic equation with a non-homogeneous equation, we will have a f on the right hand side. So the property of the fundamental solution is really important. Okay. So in particular, the following theorem, theorem 11.6, says that if the linear partial differential operator with constant coefficient has a fundamental solution E whose restriction to this open set RD with zero removed is C infinity. Okay. So from the previous fact, we know this fact 11.3, we know that every non-trivial PDO with constant coefficient has a fundamental solution. But here we actually require the fundamental solution to be C infinity outside of the point zero. Okay, so it's this is our assumption. If this is true, if we can find such a solution, such a fundamental solution, then for any omega, any open set omega, the equation 2 has a solution which is C infinity in omega, as long as the this distribution f is actually C infinity function in omega. Okay, so this is not at all trivial, right? So we only have the partial derivative, a certain partial derivative of u is equal to a C infinity function, and we can prove that this u has to be C infinity. So this is not a trivial fact, but if we have if we can find a fundamental solution with this property that the fundamental solution is C infinity outside of zero, then it is true. So now let's do this. So we consider, let's give a proof of theorem 11.6. So let's start with a U solve this equation. Right? So PU is equal to F. And F is C infinity function in omega. Omega is open set. So our idea is to show that for any epsilon x0 in omega, so the idea is to show that for any x0 in omega, we show that U is C infinity near x naught. If this is true for any x0 in omega, then we are done. By the gluing principle, we can put things together, and we show we show in each small neighborhood of x naught, for every x naught, U is C infinity. Then necessarily U is C infinity in omega. Okay. So to this end, let's consider a cutoff function. So chi be a cutoff function, which is nothing but a C infinity with compact support function equals to 1 near a neighborhood of x naught. Near x naught. So then we can deduce that chi u would be equal to delta naught chi u, and delta naught is nothing but PE because we have a fundamental solution E, Chi-U, and we can pass the partial derivative to the Chi-U. This is what we have. Another formula for Chi-U. This is a localization of the distribution U, right? Chi is just a cutoff function which preserved all the properties of U near the point x naught. Okay, and another way to write it by using this formalism with convolution, we can write it as the convolution of E, the fundamental solution, with P of Chi-U. Okay. So now, since we know that chi is a constant near x naught, we can necessarily write P of Chi-U as chi times P of U, basically. Just Pu plus R with the property that so I'm gonna precise the R, the property of R later, but for now, how do we see this kind of formula? This is actually just a Leibniz rule. So we know that we have a product of 2C infinity, not 2C. We have the partial derivative of a product of a distribution by a C infinity function. Okay, so this is well defined. And for this kind of product, we have Leibniz rule. We can we pass the partial derivatives to each of the. We can write it as a linear combination of partial derivatives of chi times partial derivatives of U. And the point is that this guy is a constant near the point of interest x naught. Chi is constant. So whenever we pass a certain partial derivative to the function chi, we have 0, right? So essentially, the contribution of the partial derivative is coming from is coming from here, right? It's just a constant function near the x point, the x naught, the point x naught. It's just a constant function times 1 multiplied by partial derivatives of u, and this one will be will not contributing near the point x naught, right? So what I just said can be formulated as follows. So the property of this R, so this R will be a distribution with compact support. And the reason is that this guy is a distribution with compact support. The partial derivative is also distribution with compact support. And this guy, chi function, is a distribution of compact support. It's a C infinity function with compact support. So product becomes the support is also included in the compact set. So this is also that way. And the point x naught is not in the support of R, okay, as I just said. So whenever we have a partial derivative with respect to so basically we write this linear combination in the Leibniz rule. We split it in two parts. When we put all the partial derivatives to U, we have this term. And when we put at least one of the partial derivatives to R, we have to chi, we have the term R. And in that case, necessarily because the property that x is a constant near x naught, this guy will be 0. So x naught is not in the support of R, as desired. Okay, so all that for the following to hold. So if we compute chi-u, and we can just compute E convoluted with P of chi-u, but P of chi-u is nothing but chi pu plus E convoluted with R. Okay, there are two parts. And our first observation is that this guy, we can just replace this is Pu by F because this is the solution, right? And we already assumed that F is a C infinity function, chi is C infinity function, so the whole thing is a C infinity function with compact support. And the convolution of a distribution with a C infinity function with compact support is always C infinity. So the first piece is C infinity. Very good. So of course it's near x naught. And on the other hand, it remains to show that this guy is C infinity near x naught. Is that true, right? So this is the key question. So let's do this. Of course, the answer would be yes. So in order to show that, we are going to take another cutoff function, theta, cutoff function near the point 0. And since we already know that x does not belong to the support of R, we can choose the support of theta so small such that x naught does not belong to the support of R plus the support of theta. So here's the idea. So we have a support, R has support, has a compact support. This is the support of R. And this here is x naught. And since x naught does not belong to this compact set, there's some certain distance, right? So if we choose the support of theta sufficiently small, the sum of these two sets will be just enlarged a little bit without containing the point x naught. Okay. Here's the maybe just slightly thicker, but still not thick enough to contain the point x naught. Okay, so this is an important point because then we can argue that E convolve with R, which is nothing, which can be decomposed as E times the theta cutoff function times E convolution with R plus 1 minus theta E convolve with R. Okay. Observation is that this guy will be 0. We notice that theta E convolution with R is equal to 0 near the point x naught because this theta E R applied to a function which has support in R, phi has support included in B epsilon x naught. It's a really small support in here for some small epsilon. If phi has support very close to this one, and we know that this the product is support included in we already know that this if the support of phi is very close to x naught, and x naught does not belong to the support of R plus the support of theta, which contains the support of a convolution, necessarily the bracket is equal to 0. Okay, so we know that support of this intersecting the support of this is empty, implies the fact that the bracket is equal to 0. So we do have this property for the first guy. And for the second, hence ER is just 1 minus theta, E convoluted with R. But this guy has the nice property that it is the convolution of R with the C infinity function. This is because we have removed the singularity, right? So 1 minus theta equals to 0 near the point 0, and E is a function. We know that E is the fundamental solution, which takes which is the C infinity in the open set RD minus 0. Okay, so we remove the singularity. The product will be a C infinity function. Then convoluted with any distribution gives us again a so this convolution makes sense because R has compact support. Okay, and convolution of R with a C infinity function will be C infinity. And this finish the proof because this is true for all the x naught, and we are done. Okay, so now let's move on to a few
interesting applications. So the first application is the property of the harmonic function, actually. So if you satisfy this Laplace equation, so what do we call Laplace equation? Just Laplacian u is equal to 0. Then necessarily u is a C infinity function in the open set omega, and that is because 0 is obviously a C infinity function. Okay, so we just apply theorem 11.6 to the function f equals to constantly equal to 0 in any domain omega. And then we know that solution must be C infinity in omega. And of course, in order to make use of this theorem 11.6, we need to make sure that the Laplacian has fundamental solution which is C infinity outside of 0. But this is the case because we have already shown that the fundamental solutions takes this form, which are clearly C infinity outside of 0. Okay, so we're all good. So just maybe for the sake of completeness, give a proof of 11.7. So proposition 11.5 says that the fundamental solutions of Laplacian is C infinity in RD with 0 removed. And the theorem 11.6 says that applied to f constantly 0 in any open set omega gives the result. Okay, and all the functions satisfying the Laplace equation will be called a harmonic function. The harmonic functions are all C infinity functions according to this corollary. And there are many other interesting properties of harmonic function, and one of them, okay, so it will be this mean value formula for the harmonic function. So it says that harmonic functions is completely smoothed out. So if we want to evaluate harmonic function at any point, we can just take the average of that. Just take the average of the function in any ball centered at that point. And do the average, we necessarily obtain the value on the function. So this is quite a specific property that is satisfied by the harmonic function. So let's show this result. 11.8. Okay. Oop. So without loss of generality, of course, we can choose x naught is equal to 0. So if we can always do a translation, right? So everything doesn't everything doesn't change. So we can just consider this at point 0. Then, so our idea how to show this kind of formula. So we are going to write the left-hand side. So here's the idea. A point-wise value of the harmonic function, we would like to write it sort of a approximation of the integral. So if we take an epsilon sufficiently small, for instance, and we do this, and we're going to, okay, this is kind of artificial. So first thing I want to do is to write it as a phi of any w epsilon. So this w could be anything in SD minus 1, right? It's just the unit surface. And if we take the value, take the limit of phi of w epsilon, when epsilon goes to 0, because of the continuity of phi, this will converge to phi of x naught. Okay, x naught is just 0, right? So doesn't matter. So these, of course, we can write it differently if we want to make use of it, because we want to make appear this integral. So our idea is to do the integration on the unit sphere, right? So sigma d w, then divided by sigma of s d minus 1, right? So the total mass of the unit sphere. So we do this kind of average, we should still be able to find the limit still hold for the same reason, right? So we have this. This is just a dominated convergence theorem. So if we can compute the difference of these two quantity, and we make epsilon goes to 0, we can see that this goes to 0. But this formula is much more informative than the left-hand side because this is super close to what we want to show. Right? So what we want to show is that you would take the average for any r, any radius. Then here we take the average on any circle, or okay, in 2 dimensions a circle, in 3 dimensions a surface, higher dimension is hypersurface. We do the average for any surface value, and then we can find back the value on the point in the center of the surface. So this guy is very close, and this is a reminiscence again of the Green's formula. So we're going to make use of that formula, this lemma 11.4 that we have used in proving the proposition 11.5. So as before, let's consider this domain, which is the big ball minus the small ball. Okay, so BR just the ball centered at 0 of radius r. B epsilon is the ball centered at 0 with radius epsilon. So now, so we want to compute here. So fundamental solution of the Laplacian that we know from proposition 11.5, Laplacian phi minus phi Laplacian E. So this guy should be 0 because, okay, of course not always true. If we consider the integral on this domain, it is true. And that is because the fundamental solution takes 0 value on any open set with 0 excluded. So this guy will be 0. So here, the fundamental is okay. So the Laplacian of phi, because phi is a harmonic function, the Laplacian phi is equal to 0. And the Laplacian of the fundamental solution in any domain which do not contain 0, open domain which do not contain 0, is equal to 0. That's a property of the fundamental solution. So this guy is 0 minus 0, which is 0. But we can make use of this the thing we have used already. We can write it differently, and it is going to be the boundary of this domain, omega r epsilon, E gradient phi, and this is a unit normal vector field minus phi gradient E and unit normal vector field pointing to the outside. Sigma, I just write d sigma. Okay, this is our integral, and we would like to approach, of course, this kind of quantity, right? So we are still some way to go. So we observe that. So if we do the integral on this surface of radius r, which is one of the boundary, there are 2 boundaries, right? The first boundary is the surface of radius r, another boundary is surface of radius epsilon. So if we do the integral on this first boundary, SR, gradient phi, if you just do this calculation and make use of the Green's formula again, we have BR. BR is the ball centered at 0 with radius r, Laplacian phi. Okay, and this we know because phi is phi is a harmonic function, so this is equal to 0. Similarly, if we compute as epsilon gradient phi, yes, the same thing. And we should also equal find 0 because it becomes, of course, now the meaning of this this vector and this are different. Okay, so there's pointing to the origin. This time the outside is actually pointing to the origin. So this here we have this negative sign with b if shown Laplacian phi, and this is again equals to 0 because phi is a harmonic function. So why this matters? This is because this E function is actually isotropic. Okay, E is isotropic, and also this gradient E is isotropic. These two things are isotropic function. So on the surface, it takes the value of these two guys, does not depend on the position of the unit vector, the position, the direction of the vector. It depends only on the length of the vector. So it depends only on R or on epsilon, these two guys. So we can actually pull it out. Nothing here. And there's a dot product. Okay. So the point is that we can actually forget about this guy because we can pull it out. And so the idea the idea is that we have the following. So this R epsilon, if we compute phi gradient E and the sigma dx, so this will be equal to 0. Okay, so these two property satisfied implies that because we can pull out this guy, this whole thing will be equal to 0. So what we have is that the integral on the boundary of this guy is equal to 0, and this is what we put in this formula. But this is almost, we're almost done because we can write it explicitly. So recall that this gradient of E, so we need some explicit calculation. So this is just some constant A depend on D, X over X to the D. Okay, this is the way we did this calculation before. And also N, the unit vector field point to the outside is actually given by X over R if X belongs to the surface of radius R, X over epsilon with a negative sign if X belongs to S, the surface of radius epsilon. So all this can be useful to evaluate this quantity, and we're going to have the following formula. We're going to have this SR phi, okay, AD, so here we should put this gradient of the fundamental solution, and here we got AD X over R to the D, right? Inner product X to the X over R, which is the unit vector field, and sigma dx, yes. And on the other hand, because this is we have this the same kind of quantity but with a negative sign, so we can put it to the other side. We have the equal to S epsilon phi AD X over epsilon D X over epsilon sigma dx. Okay, so obviously we can forget about this constant, which is irrelevant, and we are almost done. So this implies the following. We can pull out this 1 over R to the D, 1 over R to the D minus 1, right? Because okay. Just to check one thing. So the gradient of E that we consider satisfies X over Indeed. Okay. Yes, there's no problem. Yes. Okay. So now we can put things together and prove that phi x and sigma dx. All right. So we did some simplification, of course, because the inner product of x with x provide r square, and this cancels with one of the cancels with some of the r squares in the denominator. It remains only 1 over r to the d minus 1, and this is the left hand side. And the right hand side, similarly, we have this 1 over epsilon d minus 1 integral s epsilon phi of x sigma dx. Okay. And if we take epsilon goes to infinity, it goes to 0. First, of course, we do a variable change. It becomes integral on the unit surface phi of epsilon w sigma dw, and this disappear because of the change of variable. This is a measure on the d minus 1 dimensional space. So we remove the factor 1 over epsilon to the d minus 1, and this necessarily goes to phi of 0 by continuity of phi and sigma of s d minus 1. Okay, so now we can put this guy to the left hand side of the equation, and we are done. So this exactly says what we want to show, which is phi of 0 equals to 1 over the sigma, the surface measure of SR. Then we take the integral on SR of the phi function with respect to the surface measure. Okay, so here, of course, I put this guy together with this thing. We write it differently. Phi of SR, okay, SR, phi of x, sigma dx, as desired. This is actually the second formula in the mean value formula, the second identity in the mean value formula, and from this we can derive the first claim, and that is because if we compute integral, we can relate it to the integral on the ball. We can make a variable change and relate it to an integral on the surface. So 0r and s little r phi of x sigma dx d little r. Okay, this is a variable change. And here, obviously, we have phi naught then sigma of SR because of the formula, because of the mean value formula for the surface average. And we can pull out this phi naught, then 0r sigma SR dr. But this guy is nothing but 0r, then SR indicator B capital R X. Sigma x dr, right? So now we can put back to the Euro Lebesgue integration with respect to Lebesgue measure in RD of BR, which gives the volume of BR. And this is what we want. The whole thing is phi naught BR, the volume. Then we can put this thing back to the other side. We have established the average formula for volume average, and proof is done. Okay, so this is a very nice formula, and there are some necessary applications as well. Let's consider 2 of them. So the first application is called a maximal principle. So it says that if a harmonic function attains its maximum inside an open set, then necessarily it is a constant on the whole open set. So this actually makes sense, because if it takes the maximum inside, since this value, the value of the harmonic function on any point is the average is the average of the function itself in the ball centered at the point. This is the maximum means that all the neighbors will have to take the same value. Otherwise, we cannot have this averaging property. So to prove it more rigorously, let me just write down a few lines. So we consider any y in omega such that this phi of y is the maximum, or phi of let's take the supremum, okay, supremum of x in omega. So by the previous result, it's a mean value formula. We know that phi of y, and we use the first identity, this is volume average. BR, the volume of BR integral, BR centered at y, phi of x dx. Okay, so this is a property that is satisfied by harmonic function. Of course, for any R such that BR closure is included in omega. Okay, so this would imply that the integral of phi y minus phi of x dx on the set is that this would be equal to 0. Okay, we just write this guy also in this form with a constant phi y as an integrand, so that we have this this identity. And since every one of them will be larger than or equal to 0, so the integrand is larger than or equal to 0, and the integral is equal to 0, the only way to make that happen is that phi y is equal to phi of x for any x in the domain. Okay. Of course, this is true for almost every x in the domain BR, but phi is a C-infinity function as a harmonic function, so we have identity everywhere. So now that we know this is true at least for a disk centered at the maximum y with radius r, then we can find for any z in omega, we can find a chain of disks or balls connecting the z and the y. So this is the idea. We have omega, and in the ball they are all equal. This is y. And if we consider any point in z, we can find a sequence of disk connecting these 2 points z and y. And by repeating our argument for this y, the disk around y, we can do this for y, then do this for another point. We can do this for another disk, right? For this point, we also have that property. And since it is intersecting the disk centered at y, they all have the same value. We do this over and over again until we can cover the point z. So doing the trick for each of the balls gives phi of z equals to phi of y. So the proof is done. Okay. So the first property is the maximum property, and this property is quite useful. This can be used to show this uniqueness of the solution of certain PDEs. So the second thing I want to say is this Liouville theorem. It's also in the same spirit. If we have a harmonic function that is converging to 0 at infinity, then necessarily it is a constant d0. Okay. So let me just write corollary 11.10. Okay, this should be a familiar theorem in complex analysis, but here still, let me give a one-line proof. For any x in Rd, so the goal is to show that u of x, okay, the harmonic function u of on the point x, takes the value as small as possible. If you take the absolute value of the u of x, and since we know it must be the circle average or the surface average of the function itself, and for all the points far apart, all the points close, very far away, we know that the function actually decays to zero. And this implies the function cannot be very large, right? So to do this more rigorously, just take any epsilon larger than zero. Then for any r sufficiently large, u of x must be the integral of, so this is the average. Let me use this average, surface average, s d minus 1. So r actually, not s d minus 1, is the surface centered at x with radius r. And we compute u of y sigma dy. Okay, so this is the mean value. This is the mean this what is called this mean value formula. So since r is super large, so that the value u will be very small. Okay, on every point y belonging to the surface centered at x with radius r. So the point is that, so this is a certain average. Every point uniformly small, smaller than epsilon. So since epsilon is arbitrary, this shows that u of x has to be 0. And this is true for any x, hence u is identically 0. Okay, this is it. So the last thing I want to do in this lecture is to consider a Poisson equation. Now, Laplace equation is gradient Laplacian u is equal to 0. And the Poisson equation is Laplacian v is equal to something non-zero, something some distribution. So this is actually the general case, the non-homogeneous case. So we are particularly interested in the case of a three-dimensional space, which is originated from this electrostatics. The right-hand side rho is known as the charge density, and the v is called as unknown potential. So given a certain charge density, which decays at infinity, so in particular, we can choose a rho to be a distribution with compact support. So charge density is compactly supported, and we would like to know this potential induced by the charge. So we would like to solve this PDE, right? So the conclusion is that if we consider rho a compact support distribution, then there exists a unique solution that is vanishing at infinity. Of course, in order to make sense of this, we can also show that there's a unique solution satisfying the property that it is a C infinity outside of support of rho and vanishes at infinity. Okay, outside of the support of rho, we can make sense of pointwise evaluation of the distribution, since it is C infinity, and we want that to decay at infinity. And there's only a unique solution of this kind in the space of distributions. Also, this is given by the convolution formula. More precisely, we have this kind of asymptotic expansion at infinity. So there are several things. Let's do them one by one. So first, we show the uniqueness. So suppose that U1, U2 both satisfy the requirements, meaning that it is C infinity outside of supportive rho, and it decays at infinity. Both decays at infinity. Since the U minus U2, if we take the Laplacian of this, because both satisfy Poisson equation, the Laplacian will be equal to 0. So it is a harmonic function. And U1 minus U2 decays at infinity. This is not good. Let me just give a more precise meaning of that. This goes to 0 as x goes to infinity. Okay, because both satisfy this property, the difference will also satisfy this property. And according to Liouville's theorem, a harmonic function decaying at infinity is constantly 0. U2 by Liouville. And we're done with the uniqueness. So the existence part is actually simple because we already know that this convolution of the fundamental solution, this is exactly the fundamental solution in 3 dimensions. Fundamental solution convoluted with rho, the charge, gives the solution, right? So the existing solution is guaranteed. So now it remains to show the properties satisfy the solution. So we're going to check that the convolution is C infinity outside of support of rho and vanishes at infinity. So we check the properties. Well, there are several things. So existence is done. Okay, so we check the properties, and the first property is actually the regularity. So we're going to show that it is C infinity outside of the support. So if x naught does not belong to the support of rho, necessarily we can find a small radius, right? So such that BR x naught intersecting the support of rho is empty set. Okay, here is x naught. This is the support of rho. So we can find a small ball which is disjoint from the spot of rho. So for any phi, so test function, let's evaluate. Let's evaluate this V of phi, right? So V of phi, according to the definition, is the fundamental solution convoluted with rho phi, and it is according to a formula that we proved for convolution. It can be written as rho tilde is the extension of rho to the extended test functions. So this is act on the y variable, and E x, right, act on the x variable of phi of x plus y. So this is what we have. And here, if we look at this term, we can write it as the integral of E of x, because E is a L1 log function. So phi of x plus y dy. We can make a variable change so that it becomes x minus y phi of x dy. It's an integral on x variable. Sorry, it's a typo. On x variable. Exactly. So now we can interchange the order of a bracket with the interchange the order of a bracket. Okay. And an integral to have that E x minus y phi x dx. And the whole thing makes sense because that so this whole thing makes sense because this fundamental solution is actually a C infinity for all the y's in the support of rho. For all the, so here, for any x in the support of phi, which is contained in BR of x naught, the function EXY as a function of y is C infinity, in the support of rho. Okay, that's the point. So that this kind of term actually makes sense. So this rho has a compact support, so we're all good. So compact support, C infinity function in its support, so this is C infinity function. So this actually shows two things. We started out by considering V applied to phi, and we ended up having integral of a certain function times phi. So this means V of x is nothing but rho y applied to E x minus y. Okay. Okay, forget about the y, just use the dot. So rho applies to dot variable. So this is what we have, and we already showed that it is equal. It's actually a C infinity function. So both properties, so it's property, the property is satisfied. So in order to finish, so we already showed the regularity. Another thing we need to show is the decay property. So it remains to show the decay property. And we're going to do something more precise. Instead of saying that it decays at infinity, we're going to give the rate of decay, which is given by this asymptotic expansion, right? When x goes to infinity, this goes to infinity with the rate of 1 over x, basically. The leading term is 1 over x. Okay, so how to do this? So we first notice that this formula, let me be more precise, this actually becomes 1 over x minus dot. So what we want to show is an expansion of this function as x goes to infinity for any y in a support in a compact set, because we only care about compact set because the rho has compact support. Okay, so for any k compact subset of Rd, y in k, we want to expand this function x maps to 1 over x minus y, with x goes to infinity. So first we realize is x minus y is just x squared plus 2x y's inner product plus y Euclidean norm squared, whole thing square root. We can pull out this x Euclidean norm of x, then it remains 1 minus 2xy inner product divided by x Euclidean norm squared minus y Euclidean norm squared divided by x Euclidean norm squared, whole thing square root. So since 1 minus a negative a half, so it's just the parenthesis, has the expansion that 1 minus a half a plus this a square plus etc. a cube. We can make use of this to have the following expansion. Now it is equal to 1 over x, then 1 over this square root of 1 minus something, and we can make use of this. But the point is that after doing some calculation, okay, let me just give directly the result, okay, this elementary stuff. So x inner product of y divided by the Euclidean norm squared minus plus just a big O of 1 over x squared. So this term is actually of the order 1 over x because there's an x in here, and this term, there's a remainder as of the order 1 over x squared. It's a smaller order. Okay, so now, so this whole thing implies that v of x can be written as 1 over 4 pi. It's just a constant that we pull out from the fundamental solution. And rho, there will be a 1 over x, of course. We pull it out as well, and it remains rho applied to tilde apply to 1, but you know, this actually rho has compact support, so we can forget about the extension, so we can always make sense of this. Plus this x squared sum of I from 1 to 3, because three-dimensional space, rho applied to y, yes, y I xi. That's because we have this x1, y1 plus x2, y2 plus x3, y3, and when we apply rho to this, and x as rho applied to the variable, okay? So we can pull out this xi's, rho applied to each one of the yi's, so we have this formula. And this is it. So eventually we have the third term would be some term which is of smaller order. And this is it. And this is exactly what we want to show, right? That's the first thing, rho apply to 1. And the second thing is of the order 4 pi x cubed I from 1, 3, rho yi xi plus a small order term. So it decays with the rate 1 over x to infinity. In particular, it goes to 0 at infinity. This is done. All right, this is it for today. See you next time.